Okay, we're continuing with more example problems from the Taylor and Maclaurin series section. In this video, we're going to evaluate this indefinite integral as an infinite series. Okay, so what we want to do is first express the integrand as a power series, so as a Taylor series, and then integrate that Taylor series, which is completely valid, right? We know how to integrate any power series, and we know how to express a function like this as a power series. So let's start by expressing this as a power series. Okay, so how would we express this as a power series based on the previous example problem videos? How could we do this? Well, we could go from scratch, just use the definition of the Taylor series, or what would be easier, what you should do if you can, is use a base function. So we can, this has the form of a binomial series. So if we write this as 1 plus x cubed to the 1/2, then we see that this has the form of the binomial series with the variable x cubed and k 1/2. Okay, remember with binomial series, there's no center point. The binomial series was developed, it's centered at 0. So it's just with the binomial series, it's all about just pattern matching. It's pattern matching, and it's centered at 0. Like if you look here, it's not x minus something, it's x minus 0. It's the a is 0. Okay, so this is just matching this up. We've got the k is 1/2. Okay, then x cubed to the n. Okay, so that's it. But unfortunately, as if you recall from the other videos, the binomial series isn't as easy to work with as far as, for other pattern matching, like using other base functions, we could just input that directly into the power series base formula and we were done. With the binomial series, we want to expand this out, expand the first few terms out, and then identify a pattern. So it's not a big deal, it's just a little more work. So, okay, we can see here that if to write out the first few terms, we've got 1 plus 1/2 x, and then we'll have 1/2, the k times k minus 1 will be 1/2 times 1/2 minus 1 is minus 1/2, so this will be minus, and then with binomial series, we can do this to identify a pattern. So it's going to be 2 times 2 times 2 factorial, and then just a 1 in the numerator, right? It was 1/2 times minus 1/2, and then x squared. Okay, now there should be a plus, because we're going to have 1/2 times something negative. Okay, so it's going to be 1/2 times minus 1/2, and then what is 1/2 minus 2? 1/2 minus 2, it's 1/2 minus 4 over 2. That's going to be minus 3, but it ends up just being positive 3 in the numerator. So, okay, we're going to have 2 times 2 times 2 times 2 factorial, and then 1 times 3 x cubed, and then negative. And now, so I'm assuming that 1/2 minus 3 is going to be 5, or minus 5/2. So, yeah, okay. So we see the pattern. This is going to be 2 times 2 times 2 times 2 times 2 factorial, and then 1 times 3 times 5 x to the 4th, like that. Okay, so we can write this as, let's do 1 plus 1/2 x plus, and then we'll do from n is equal to 2 to infinity, and then we need to get the alternating term minus 1. This first term is going to be positive or negative, so we'll do n minus 1. Okay, and then it's going to be, so 2 to the n times 2 factorial, which is just 2. So what we've got is this is, let's do this. So 2 cubed, 2 to the 4th, 2 to the 5th. So, okay. 2 to the n plus 1, and then, well, let's do the numerator first, actually. So, okay. We're going to have 1 times 3 times 5, and then, okay, so we start at a sub n, we start at 1 plus 2, and then n minus 2, because the first term is 1 and we're starting at n is equal to 2. So n is equal to 2, you've got 1. N is equal to 3, you've got 3. So yeah, so this is 1 plus 2n minus 4, 2n minus 3. Okay. So 2n minus 3, and then 2 to the n plus 1, then x to the n. Okay. Now the radius of convergence is what? Well, okay, we don't have to do the ratio test here because all we did was substitute x for x cubed. So if the radius of convergence is equal to 1, then we just set, that means the absolute value of x is equal to is less than 1. So here we've got the absolute value of x cubed is going to be less than 1. Okay, based on absolute value inequalities, this means this here, raise everything to the 1/3 power, minus 1 to the 1/3 is minus 1, so the radius of convergence is 1. So let's go ahead and let's put, so okay, 1 plus, let's just box this in. So radius is equal to 1. Okay. And, you know, that's kind of a downside to having to use series for something like this, is that, you know, in this situation, we'd only get the integral for x. X is something from between minus 1 and 1, right? So, like, in general, if we could just get this integral with normal integration techniques, then you just do that. But the idea is maybe you can't get the integral. So the next best option is you can get something like this. It's better than nothing. Okay. So now let's go ahead and integrate this power series here. And, you know, maybe this actually is hard to integrate by regular means. Just looking at it, I'm not sure how we would integrate this. You know, you could think maybe a trig substitution, but this is not x squared. So that's probably why the book gave this example, because most likely these, like an integral like this, is maybe you can't get the integral. I mean, let's see. So, okay, the square root of 1 plus x cubed, store that as e. Okay, now we want to integrate e with respect to x. Yeah, so it couldn't even give us an official answer. We still have an integral in here. So yeah, but we can still find this integral as a power series at a distance of plus or minus 1 from x. So, all right, so let's integrate the power series. So we integrate this. This is x. We integrate this. This should be 1/4 x squared. Okay, now we'll go ahead and write the integration constant. And then let's integrate the power series. How do you integrate a power series? Well, that's really easy. It seems intimidating, but you're just coming into the entire a sub n, including the x, and just integrating with respect to x. And so the reason why it's easier than it looks is because all these n's, you treat them as constants. So, okay, now with differentiation, you have to think about maybe the starting point goes from n is equal to 2 to n is equal to 1. Sometimes it would, sometimes it wouldn't. You have to look and see if the actual first term is a constant term. But with integration, this is no matter what, it's going to stay at the first term is not going to change. There's no terms are going to get eliminated. Okay, and so this is x to the n. That's as easy as it gets. You just change this to x to the n plus 1 and then put an n plus 1 in the denominator. And so what we'll do is we'll do, so bring the n plus 1 here. Well, let's do the numerator first. So 1 times 3 times 5. Okay. And then n plus 1 to the n plus 1, then x to the n plus 1. And then the radius of convergence when you integrate or differentiate doesn't change. Okay. Now, okay, I'm putting equals here, but it's almost implying like these two are equal. This is this. Okay. And we can do, let's actually bring the c out front. So x plus 1/4 x squared. So c plus x plus 1/4 x squared. And you typically you'd put the c over here, right? But it's just that would create confusion with the sum is all. Okay, and that's it. It's that simple. Now, as far as the c, we can't determine that here because with the times that we determine the c, we could integrate this, get an integral, and then you plug in any x you want, which would usually is the center point, so you can eliminate all the infinite terms. You plug in that same x over here, and then you solve for c. But there's no, we can't evaluate the integral. But still, this is still fine because when you do an indefinite integral in general, you always have a c anyway, right? Like if we were actually able to evaluate this, we'd have a c anyway. So this makes sense. Now, actually, we could check if n was equal to 1, what happens? You have x squared and then 4 in the denominator, and then you have a 2 down here. What do you get up here? So no, we can't. We worked problems where sometimes you would check, and n is equal to 1, you actually get this term, so you could actually put this into the sum. But no, we have to leave these out here. Yeah, and the radius of convergence again is 1. And actually, let's go ahead and do another one. So let's evaluate this. We can get the series, the infinite series of cosine x. We just get it straight from the table, the Maclaurin series table. And you might be wondering, well, do we use a Maclaurin series or a Taylor series? Whatever you want. Because remember, like the Maclaurin series for cosine of x is just some power series. The Taylor series of cosine of x centered at whatever is just another power series. But it's all the same. As when you go to infinity, it's all cosine of everything's the same. So you pick whatever's easiest. It would depend. For example, it would depend on if the radius of convergence wasn't infinity, then it depends on where you want to evaluate this integral, right? So, okay, cosine x as a power series, Maclaurin series, is okay, minus 1 to the n, x to the 2, and over 2 factorial. Okay, so now let's subtract 1 from this. So, okay, we would do, the idea is you do this. We subtract 1 from both sides. So cosine x minus 1 is equal to, this whole series minus 1. Okay, so how can we think about this? What can we do here? Well, okay, let's look at the first term. when n is equal to 0, you've got, this is positive, 0 factorial is 1, x to the 0 is 1, you just get 1. So we can think about this 1 would get rid of that first term. So all we need to do here is this. Right? This is the cosine of x, the cosine of x series, but with the 1 taken out, the 1 in the beginning taken out. That's perfect. Okay, now let's divide both sides by x. So we've got, this would be, we could just multiply that by 1 over x. Okay, so now we bring in that. So, okay, you've got x to the minus 1, so that's x to the 2n minus 1 over 2n factorial. Now, remember, here you have to be careful because, you know, when you multiply like some x expression by a power series, you can't just do that for with any x expression. You can do it with any x expression as long as what results after you simplify is a power series from the same start point to infinity. We've talked about this before. It's not like I could multiply this by whatever I want, simplify, and that's a valid, that is a valid action I've done to the power series. The issue that comes into play, though, is that it's this equality here. These two being equal, we haven't talked about how to we haven't ventured off. All of the proofs we've done have been strictly associated with power series. So we couldn't have multiply by something and it changes to where the first few terms are on a power series, but then after that, it's still a power series. We have to go back and reprove again that the equality here. But since we can see, though, okay, n is equal to 1, this is going to work out because if this was just x to the n and we were starting at 0 and you multiply by 1 over x, then the first term is going to be like x to the minus 1. And that's not a power term. So it's not a power series anymore. Here, because we have the x to the 2n and because we're starting at 1, we're okay. Because, okay, you plug in 1, what do you get? X to the first, and then everything else after that is just increasing power, so we're good. Okay, now the radius of convergence, let's go ahead and get that. So, okay, since we multiplied, we could usually just go reference like cosine of x, which should be infinity. Yeah, it's infinity, but yeah, so the radius of convergence is infinity, but since we did all this stuff here, subtract 1 divided by x, I want to check again. I'm not sure what the mathematical rules are for. All we know is that if all you strictly do is just integrate or just differentiate, the radius of convergence doesn't change. Or if all you do is just like take cosine of x, power series, and swap in something for the x, then it's the same radius of convergence, but now you set like this, the radius of convergence is infinity. So now the radius of convergence would be that it would still be infinity because like you would, okay, let's say the radius of convergence hypothetically was 1 here or 2. Then you would say that means that the absolute value of x is less than 2. That's what this means. So here you would say the absolute value of x cubed is less than 2 and solve for x. That's the idea there. But anything outside of that, differentiating, integrating, or doing a pattern match, we haven't talked about. So the point is that since we subtracted 1 divided by x, we're just going to go ahead and just use the ratio test to get the radius of convergence here. So, okay. The minus 1 to the n goes away, and you've got 2 times n plus 1 minus 1, 2n plus 2 minus 1, 2n plus 1. Okay, so x to the 2n times x over 2 times n plus 1 that's 2n plus 2 factorial. So let's do 2n plus 2, 2n plus 1, and then 2n factorial. Okay, then we've got 2n factorial, x to the 2n times x to the minus 1. And this is x to the first. Okay, so what we get here is ends up being x squared, right? It's kind of confusing, but imagine bringing this into the numerator, and then x to the 2n goes away. So we've got, and then, okay, now this is the absolute, this is always positive for all n and x. Okay, limit as n goes to infinity of this is 0 for all x. So, okay, the radius of convergence of this is infinity. But it's still, you can imagine, it's still, you can't plug in 0. Even though this converges to at 0, if you plug in x equals 0, that's not a part of the domain, though, because that's not part of the domain of this. Right? It's kind of like a derivative. If you've got the derivative of, there's some derivatives where once you take the derivative, the resulting derivative, you can plug in like a certain x and you get an answer, but that x was actually not valid in the domain of the original function. So it's automatic rule. It doesn't matter if you happen to take a derivative and there's an x value that you can input and get a value. If it's not in the domain of the original function, then it's not part of in the domain of the derivative. All right. So the integral of cosine x minus 1 is, so, okay. Let's put the c. All right. Minus 1 to the n, and then 2n minus 1 plus 1 is x to the 2n, and then we'll have, so it's going to be, yeah, x to the 2n over 2n. So let's do this. 2n times 2n factorial, and then x to the 2n. And there you go. Where the radius of convergence here is infinity.